On the 27th of December, 2024, while most of the world was still digesting holiday meals, exchanging gifts, and wrapping up the final lazy days of the calendar year, a telescope in the Chilean desert quietly recorded something that would soon dominate headlines across the planet. The telescope was part of the Asteroid Terrestrial Impact Last Alert System, known as ATLAS, a network of 4 robotic observatories funded by NASA and operated by the University of Hawaii. This particular station sat in the high, dry hills of Rio Hurtado, Chile, scanning the sky methodically, capturing images of the cosmos in 30-second exposures through an orange band filter tuned to wavelengths between 560 and 820 nanometers. On that night, the telescope captured 4 images over a span of about 52 minutes. In each image, there was a faint streak of light, a tiny smear where a sharp point should have been. Something was moving fast, and it was headed, at least roughly, in our direction. The object was a rock, a chunk of ancient stone and metal, forged in the fires of the early solar system roughly 4.6 billion years ago, tumbling silently through the void at a speed of approximately 17 kilometers per second. That is more than 61,000 kilometers per hour, faster than a rifle bullet by a factor of 14, faster than the International Space Station by a factor of 2. Fast enough to cross the width of the continental United States in about 4 minutes, and it had just been spotted, not on its way in, but on its way out. 2 days earlier, on Christmas Day, this object had already passed closer to Earth than anyone realized. It had swept within 829,000 kilometers of our planet, roughly twice the distance to the Moon, approaching from the sunward side where no ground-based telescope could see it. We found it only after it had already passed by, as it drifted into the night sky and became visible for the first time. The astronomers who found it gave it a name, not a dramatic name, not a name from mythology or ancient legend. They called it 2024, YR4. The Y indicated it was discovered in the second half of December. The R4 indicated it was the 117th object catalogued in that period, a bureaucratic label for something that would soon become anything but ordinary. Within weeks of its discovery, automated warning systems at NASA's Jet Propulsion Laboratory in Pasadena, California, and at the European Space Agency's Near-Earth Object Coordination Center in Frascati, Italy, began flagging it. The calculations were early and uncertain, built on just a few nights of observation data, but they pointed to a disturbing possibility. This rock, this seemingly insignificant speck of cosmic debris, roughly the size of a 15-story building, had a small but genuine chance of slamming into Earth on the 22nd of December, 2032. The initial probability was about 1.3%, one chance in 77. That might sound trivial, but consider what it means in real terms. If someone told you there was a 1 in 77 chance that an explosion carrying the force of 500 Hiroshima-sized nuclear detonations would occur somewhere along a line stretching from the coast of Colombia, through Nigeria, through India to Bangladesh, you would not shrug it off. You would not call that trivial. You would call it terrifying. And as the weeks passed, the probability did not decrease. It rose. It climbed to 1.2%, then 2.8%. Then, on the 18th of February, 2025, to 3.1%, the highest impact probability ever recorded for any asteroid in the history of modern observational astronomy. For a brief, deeply unsettling moment, 2024 YR4 became the most dangerous known object in the sky. This is the story of that asteroid. It is the story of how we found it, how close it came to becoming a confirmed threat, and what it revealed about the fragile, underfunded, and deeply incomplete state of our planetary defense systems. It is also the story of what happens next time, because there will be a next time. The solar system guarantees it. And next time, the math might not work out in our favor. By the end of tonight, you are going to understand why a rock the size of a large apartment building, discovered almost by accident at a telescope in Chile, triggered formal emergency notifications at the United Nations activated international warning networks for only the second time in human history, forced the European Space Agency to convene emergency meetings in Vienna, and compelled the world's space agencies to confront an uncomfortable truth that they had been quietly aware of for years but had never been forced to say out loud. We are not ready. Not even close. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. The designation sounds clinical, bureaucratic, 2024, YR4. But behind that sterile label was an object carrying the energy of a thermonuclear weapon, approaching our planet from a direction where no telescope on Earth could see it. By the time we found it, it had already come and gone, and the orbit that brought it close in December of 2024 would bring it back. Again and again and again, every 4 years, a celestial metronome ticking away toward a possible future encounter that might not end as quietly. Now let us begin. To understand why 2024 YR4 mattered so much, and why it should still matter even after the immediate threat has passed, we first need to understand the environment it came from. And to do that, we need to reckon with a reality that most of us push to the margins of our daily awareness. Our solar system is not the orderly, sanitized model you see in textbook illustrations. It is not a set of neatly spaced planets tracing clean ellipses around a tidy yellow star. It is messy, it is crowded, and it is, in the most literal sense, dangerous. The inner solar system, the region where Earth orbits, sits within a vast cosmic shooting gallery. Between the orbits of Mars and Jupiter lies the main asteroid belt, a broad, diffuse ring of rocky debris containing millions of objects left over from the chaotic early days of the solar system's formation, approximately 4.6 billion years ago. These are the fragments that never became a planet. Jupiter's enormous gravitational influence stirred the region so violently during the solar system's youth that the material there could never coalesce into a single coherent body. Instead, it remains as it was, a scattered field of rubble ranging from dust grains to objects hundreds of kilometers across. The asteroid belt is often depicted in popular culture as a dense, hazardous field, a swarm of tumbling boulders that spacecraft must carefully navigate. This image is almost entirely wrong. The belt is mostly empty space. If you stood on the surface of one asteroid in the main belt and looked around, the nearest neighboring asteroid would likely be so far away that you could not see it with the naked eye. The total mass of the entire asteroid belt, all those millions of objects combined, is less than 4% of the mass of our Moon. It is a vast, mostly empty region containing a relatively modest amount of material. But despite this emptiness, the belt is a source of danger for Earth. Over millions and billions of years, the gravitational influence of Jupiter and Saturn perturbs the orbits of belt asteroids. These perturbations are not dramatic or sudden. They are subtle, accumulating over centuries and millennia. A slight tug here, a gentle nudge there, and an asteroid's orbit gradually shifts. Some of these shifts push asteroids outward, into the cold outer reaches of the solar system, but some push them inward, toward the Sun and toward Earth. The most powerful of these perturbations occur at orbital resonances, specific locations in the belt where an asteroid's orbital period has a simple mathematical relationship to Jupiter's. The 3-to-1 mean motion resonance, located at approximately 2.5 astronomical units from the Sun, is one of the most important. An asteroid at this distance completes exactly 3 orbits around the Sun for every 1 orbit that Jupiter completes. This resonance amplifies tiny gravitational perturbations, pumping energy into the asteroid's orbit and gradually increasing its eccentricity, the elongation of its orbital path, until the asteroid's orbit stretches inward far enough to cross the orbits of the inner planets, Mars, Earth, sometimes even Venus. These displaced, orbit-crossing rocks are what astronomers call near-Earth objects, or NEOs. As of early 2025, more than 37,000 near-Earth asteroids had been catalogued and tracked. That is a large number. It represents decades of dedicated survey work by telescope programs around the world, including the Catalina Sky Survey in Arizona, the Pan-STARRS system in Hawaii, the Atlas network, and many others. But here is the uncomfortable truth that sits beneath those impressive numbers. We estimate that we have found only about 40% of the near-Earth asteroids larger than 140 meters in diameter. 140 meters is considered the threshold for a regionally devastating impact, an event that could destroy a large metropolitan area and kill millions of people. We have found roughly 60% of objects above this size. That means approximately 10,000 asteroids capable of regional devastation remain undetected, drifting silently through the inner solar system on orbits we have not yet mapped. For objects in the 50 to 100 meter range, the range that includes 2024 YR4, the picture is much worse. We have found perhaps 5 to 10% of the total population. The vast majority of these city-killing rocks are still unknown to us. They are too small and too faint to be detected at great distances, and they become visible only when they make close approaches to Earth, often far too close for comfort. Let us talk about scale for a moment, because the numbers involved in planetary defense are notoriously difficult to grasp without anchoring them to something familiar. Imagine you are standing at one end of a regulation football field, 100 yards of green turf stretching before you. Now imagine that this field represents the distance from the Earth to the Sun, a span of roughly 150 million kilometers, a distance that astronomers call 1 astronomical unit. On this scale, the Earth would be smaller than a grain of sand. It would be a tiny sphere, about 1.3 millimeters in diameter, sitting near the 30-yard line. The Moon would be an even smaller grain, roughly 0.35 millimeters across, sitting about 3.4 millimeters from Earth. 3.4 millimeters. That is the distance to our nearest celestial neighbor on this scale. And the asteroid 2024 YR4, at roughly 60 meters in actual diameter, would be so impossibly small on this scale that it would be invisible, not merely hard to see, invisible. You could not detect it with a magnifying glass. You could not detect it with a microscope. It would be a speck of matter far smaller than a single human cell, drifting somewhere across that football field, carrying enough energy to flatten a city. Now consider a different kind of scale. Consider time. The solar system is approximately 4.6 billion years old. If you compressed that entire history into a single 24-hour day, with the formation of the solar system occurring at midnight, then the first single-celled life would appear around 4 in the morning. Complex multicellular life would not emerge until about 8:30 in the evening. The dinosaurs would appear at roughly 10:40 in the evening and would be wiped out by an asteroid impact at approximately 11:39, just 21 minutes before midnight. The entire history of human civilization, from the first cities in Mesopotamia to the present day, would occupy the final fraction of a second before midnight, less than the blink of an eye on the cosmic clock. In that fraction of a second, we have built cities and written symphonies and split the atom and walked on the moon. And in that same fraction of a second, we have only just begun to look up at the sky and ask whether anything is headed our way. Here is another way to feel the scale. If the Sun were the size of a beach ball, about 70 centimeters in diameter, then Earth would be a small peppercorn about 30 meters away. Jupiter would be a golf ball roughly 156 meters distant, and the nearest star, Proxima Centauri, would be another beach ball more than 7,000 kilometers away. In this model, the asteroid belt would be a sparse scattering of dust grains orbiting at distances of roughly 60 to 120 meters from the beach ball Sunday, and 2024 YR4 would be a particle so small that no human instrument could detect it at that scale. A phantasm of matter drifting through the space between the peppercorn Earth and the dust grains of the belt, yet real enough to carry the explosive force of nearly 8 million tons of TNT. The energy that 2024 YR4 would have released upon impact has been estimated at approximately 7.7 megatons of TNT. This number demands context. The atomic bomb that was dropped on Hiroshima in August of 1945 released energy equivalent to roughly 15 kilotons of TNT, 15,000 tons. The explosion killed an estimated 80,000 people instantly, and devastated an area of roughly 13 square kilometers. 2024 YR4 carried the equivalent of 7,700 kilotons, 500 times the energy of Hiroshima, roughly half the yield of the Castle Bravo thermonuclear test, the largest nuclear detonation ever conducted by the United States, which was itself a partially accidental explosion that exceeded its expected yield by a factor of 2.5 and contaminated an area of more than 18,000 square kilometers with radioactive fallout. 2024 YR4 carried roughly 15% of the energy of the Tsar bomber, the most powerful nuclear weapon ever detonated. A 50-megaton Soviet hydrogen bomb tested in 1961 over the Arctic archipelago of Novaya Zemlya, and all of this energy was packed into a rock that nobody knew existed until 2 days after it had already flown past our planet at a distance less than the diameter of Jupiter. To make this more tangible still, let us look at what happened the last time an object of similar size struck. On the 30th of June 1908, a rocky body estimated at 50 to 60 meters in diameter entered Earth's atmosphere above the Podkamennaya Tunguska River in the remote taiga of central Siberia. The object did not reach the ground. It exploded at an altitude of approximately 5 to 10 kilometers in what scientists call an airburst, a mid-air detonation caused by the extreme compression of air in front of the rapidly descending body. The energy released has been estimated at between 3 and 15 megatons of TNT, with most modern estimates settling around 10 to 12 megatons. The destruction was extraordinary. The explosion flattened approximately 2,150 square kilometers of forest. That is an area equivalent to the Greater London metropolitan area, or roughly 830 square miles. An estimated 80 million trees were knocked down, their trunks snapped like matchsticks, lying in a radial pattern pointing away from the blast center. Near the epicenter, trees remained standing but were stripped of every branch and shred of bark, standing as bare, ghostly poles. The shockwave was detected by seismographs as far away as England. Atmospheric pressure fluctuations from the blast were recorded across Europe. For several nights following the event, the skies over northern Europe and parts of Asia were so bright from high-altitude dust and ice crystals that people could read newspapers outdoors at midnight. An astronomer at the Armagh Observatory in Northern Ireland noted a strange luminous glow in the sky that night, bright enough to read by, even though the moon was not visible. Eyewitnesses closer to the blast described a scene of apocalyptic intensity. Semyon Semenov, a farmer sitting on the porch of his trading post in the village of Vanavara, approximately 65 kilometers south of the explosion, described seeing the sky split in two and fire appearing high and wide over the forest. He reported feeling a burst of heat so intense that he believed his shirt had caught fire. The blast wave arrived moments later, throwing him from his chair and blowing out the windows of his house. Other witnesses described being thrown through the air. A man approximately 200 kilometers from the epicenter reported hearing a sound like cannon fire that went on for several minutes. Evenki reindeer herders near the blast zone reported seeing a blinding blue-white light, followed by a deafening explosion and a wave of searing heat. Hundreds of reindeer were killed. Campsites and storage huts were destroyed. At least one herder reportedly died from injuries sustained when he was thrown against a tree. The Tunguska object was roughly the same size as 2024 YR4, perhaps slightly smaller, and it struck one of the most remote, least populated places on Earth. If it had arrived 4 hours and 47 minutes later, the rotation of the Earth would have placed the Imperial Russian capital of St. Petersburg directly beneath its trajectory. The death toll would have been in the hundreds of thousands, quite possibly exceeding 1 million. It would have been the single deadliest natural disaster in all of recorded human history. And it would have come with no warning whatsoever. In 1908, humanity had no telescopes capable of detecting such objects, no warning systems, no planetary defense infrastructure of any kind. The rock simply arrived, and the people beneath it either survived or they did not, based entirely on geography and chance. This is the scale of the threat that 2024 YR4 represented. not the planet-killing scenario of science fiction, not the dinosaur-ending 10-kilometer behemoth that scientists now know struck the Yucatan Peninsula 66 million years ago, leaving the Chicxulub crater and ending 75% of all species on Earth. We are talking about something far more mundane and, in many ways, far more frightening. We are talking about rocks the size of an apartment building, rocks that arrive every few hundred to few thousand years, rocks that are too small to detect at great distances, too fast to intercept on short notice, and powerful enough to erase a city from the map in a single blinding instant. The system we have built to watch for these objects is impressive in many ways, but it is also deeply incomplete. The primary workhorse of near-Earth object detection in recent years has been ATLAS, but it is only one component of a much larger network. The Catalina Sky Survey, operated by the University of Arizona's Lunar and Planetary Laboratory, uses telescopes atop Mount Bigelow and Mount Lemmon in the Santa Catalina Mountains north of Tucson. For years, the Catalina Sky Survey was the single most prolific discoverer of near-Earth asteroids, routinely finding hundreds of new objects each year. The Pan-STARRS system, the Panoramic Survey Telescope and Rapid Response System, operates from the summit of Haleakala on the Hawaiian island of Maui. Pan-STARRS uses a 1.8-meter telescope equipped with one of the largest digital cameras ever built, a device containing roughly 1.4 billion pixels. Each year, Pan-STARRS discovers more than half of all near-Earth objects larger than 140 meters detected globally. Together, these survey systems have transformed our understanding of the near-Earth asteroid population. Before 1990, fewer than 100 near-Earth asteroids were known. By 2000, the number had grown to roughly 1,000. By 2010, it was 7,000. By 2020, it was 24,000. By 2025, it exceeded 37,000. The rate of discovery has accelerated dramatically thanks to improvements in telescope technology, camera sensitivity, and automated detection algorithms. But the total population of near-Earth objects is estimated to be vastly larger than what we have found. What makes the detection challenge particularly insidious is that the most dangerous objects are often the hardest to find. Large asteroids, those above 1 kilometer in diameter, are relatively bright and can be seen at great distances, giving us years or decades of warning. We have found more than 95% of the estimated 950 near-Earth asteroids in this size class, and none of them currently poses a threat. But the smaller objects, those in the 50 to 100 meter range, are thousands of times fainter. They can only be detected when they are relatively close to Earth, often during the very close approaches that make them dangerous in the first place. They are, in a sense, invisible until they are almost upon us, and by then, the window for response may have already closed. 2024 YR4 was discovered precisely because it made a close approach. It swept past Earth at a distance of roughly 829,000 kilometers on Christmas Day, 2024, and its proximity made it bright enough for the Atlas telescope to detect. If it had been on a different orbit, one that did not bring it close to Earth, it might have remained unknown for decades or centuries. It was its very proximity, the very characteristic that made it potentially dangerous, that allowed us to find it at all. The naming convention for asteroids is worth a brief explanation because it reveals something about the sheer volume of discoveries the astronomical community handles. The designation 2024 YR4 follows a system established by the International Astronomical Union. The first 4 digits indicate the year of discovery. The first letter after the year indicates the half-month of discovery, with A corresponding to the first half of January and Y corresponding to the second half of December. The second letter and any following numbers indicate the order of discovery within that half-month. The letter R indicates the 18th discovery, and the subscript 4 indicates that the alphabet had been cycled through 4 complete times before reaching R again. This means 2024 YR4 was the 117th object discovered in the second half of December 2024, 117 asteroids found in just 15 days. That gives some sense of the torrent of discoveries flowing through the system, and each one must be tracked, analyzed, and assessed for potential impact risk. It is an enormous computational and observational challenge, conducted largely by a small community of researchers working around the clock. Now consider the speeds involved in more human terms. 2024 YR4 was traveling at approximately 17.2 kilometers per second relative to Earth at the time of its hypothetical atmospheric entry. That is the speed at which it would have slammed into our planet's atmosphere if the trajectory had been slightly different. At 17.2 kilometers per second, the asteroid would cross the length of Manhattan Island, roughly 21 kilometers from tip to tip, in slightly more than 1 second. It would traverse the distance from London to Paris, approximately 340 kilometers, in approximately 20 seconds. It would cross the entire Atlantic Ocean, from New York to Lisbon, a distance of roughly 5,400 kilometers, in about 5 minutes and 15 seconds. At this speed, the journey from the point of atmospheric entry to the moment of maximum energy release, whether as an airburst or a surface impact, would take approximately 2 to 3 seconds. 3 seconds. From the first faint glow of atmospheric compression to the blinding flash of detonation, there would be no time to react, no time to seek shelter, no time to do anything at all except witness the event, if you were far enough away to survive the first seconds. For comparison, a commercial airliner travels at roughly 250 meters per second. A high-powered rifle bullet travels at roughly 1,000 meters per second. The space shuttle, during orbital flight, traveled at roughly 7.7 kilometers per second. 2024 YR4 was more than twice as fast as the space shuttle. It was moving at roughly Mach 50, 50 times the speed of sound. When an object of this size and speed encounters the atmosphere, the air in front of it cannot move out of the way fast enough. It compresses violently, heating to temperatures of tens of thousands of degrees. The compressed air in front of the asteroid becomes a ball of superheated plasma, glowing brighter than the sunday. The energy of this compression, combined with the fragmentation of the asteroid body, produces the airburst, a sudden, catastrophic release of energy that radiates outward as a shockwave, a thermal pulse, and an electromagnetic flash. The Atlas telescope network that discovered 2024 YR4 has a specific design philosophy that is worth understanding, because it illuminates both the capabilities and the limitations of our current detection infrastructure. Unlike some asteroid survey telescopes that are optimized to detect faint, distant objects over long periods, Atlas is designed for speed and coverage. Its telescopes scan the entire visible sky every 24 hours, looking not for faint, slow-moving objects, but for relatively bright, fast-moving ones. This makes Atlas particularly good at detecting asteroids that are making close approaches to Earth, objects that are close enough to be relatively bright, but moving quickly across the sky. It is, in essence, a last alert system, just as its name suggests. It is designed to catch objects that other surveys may have missed, providing a final warning of an imminent, close approach or potential impact. But Atlas has inherent limitations. Its telescopes are relatively small, with apertures of about 0.5 meter. This limits their sensitivity to fainter objects. An asteroid at a distance of 100 million kilometers might be too faint for Atlas to detect, even if it were on a direct collision course. By the time such an object becomes bright enough for Atlas to see, it might be only days or weeks from impact. For the largest objects, this is sufficient. But for smaller objects, like 2024 YR4, the window of detectability can be distressingly narrow. There is yet another scaled comparison that helps bring the reality of asteroid impact into focus. Imagine you could drive a car from Earth to 2024 YR4 at highway speed, say 100 kilometers per hour. At the asteroid's closest approach distance of 829,000 kilometers during its December 2024 flyby, the drive would take approximately 345 days, nearly a full year of non-stop driving. That is how far away it was at its closest. It sounds like a comfortable margin. But at the asteroid's velocity of 17.2 kilometers per second, it covered that same distance in less than 14 hours. What feels far in human terms is near instantaneous in astronomical terms. Distances that would take us months to cross, the asteroid covers before lunch. Now imagine the same exercise on the day of closest approach in 2032. The asteroid will pass at roughly 278,000 kilometers. At highway speed, that is about 4 months of driving. At the asteroid's velocity, it passes in approximately 4.5 hours. And the Moon, sitting at 384,000 kilometers, is only about an hour and a half further out. The gap between Earth and the Moon, a gap that has always seemed so vast, so impossibly wide, is traversed by this rock in less time than it takes to watch a feature film. The relationship between asteroid size and impact frequency follows a well-documented pattern that is worth understanding. Scientists refer to it as a power law. As the size of the impactor decreases, the frequency of impacts increases dramatically. Objects larger than 1 kilometer, those capable of global catastrophe, strike Earth roughly once every 500,000 to 1 million years. The last such event was approximately 66 million years ago. Objects around 140 meters capable of devastating a large region arrive roughly every 20,000 to 30,000 years. Objects around 50 to 60 meters, like 2024, YR4, and the Tunguska impactor, arrive roughly every 500 to few thousand years. Objects around 20 meters, like the Chelyabinsk impactor, arrive roughly every 60 years. And small meteors, pebble-sized fragments that produce bright streaks in the night sky, arrive by the thousands every single day. This pattern means that the most frequent dangerous events come from the smallest dangerous objects, the ones that are hardest to detect and easiest to miss. The Tunguska-class events, those capable of flattening a city, occur frequently enough that we should expect several within a single millennium. The fact that the last one struck in 1908, in one of the most remote locations on the planet, is not evidence that such events are rare. It is evidence that we have been fortunate, deeply, critically incomplete. And the story of 2024 YR4 is, at its core, a story about what happens when that incomplete system encounters exactly the kind of threat it was designed to detect and almost fails. The story of 2024 YR4 is not merely a story about a rock drifting through space. It is a story about the limits of human knowledge, the fragility of our detection systems, and the terrifying arithmetic of orbital mechanics. To understand what happened in January and February of 2025, and why the world's planetary defense community was genuinely alarmed, we need to understand something that most people find deeply counterintuitive. When astronomers track a newly discovered asteroid, the probability of impact often goes up before it goes down. This seems backward. Surely more data should mean more certainty, and more certainty should mean less danger. But that is not how orbital mechanics works. When an asteroid is first discovered, its orbit is known only approximately. The range of possible future positions is enormous. Astronomers model this range as a cloud of possible trajectories, thousands or even millions of slightly different orbital paths, each consistent with the limited observations available. This cloud is sometimes called the uncertainty region. At the time of the potential impact, years in the future, this uncertainty region stretches across an enormous volume of space. Within that volume, Earth occupies a tiny fraction, a very tiny fraction. So the initial probability of impact is usually very small. Not zero, but small. But as more observations come in, the uncertainty region shrinks. The cloud of possible trajectories contracts. And as it contracts, one of two things happens. Either the cloud moves away from Earth entirely, and the probability drops to zero, or the cloud contracts around a region that still includes Earth, and the probability increases, because Earth now represents a larger fraction of the remaining possible positions. This is not because the asteroid has moved closer. It has not. It is because our knowledge of where the asteroid will be has become more precise, and that more precise knowledge happens to point closer to Earth. Think of it this way. Imagine you are looking for a marble hidden somewhere inside a large warehouse. At first, you know only that the marble is somewhere in the building. The probability that it is directly under your left foot is extremely small, because the warehouse is vast and your foot is tiny. But as you search, you eliminate rooms and corners where the marble is not. The remaining area shrinks. If you happen to be standing in the remaining area, the probability that the marble is beneath your foot increases, even though you have more information than before. Eventually, one of two things happens. Either you clear the area beneath your foot and the probability drops to 0, or you find the marble and the probability jumps to 100%. In between, the probability may rise and fall as the search narrows. This is exactly what happened with 2024 YR4, and it followed a pattern that planetary defense experts have studied extensively, a pattern that was demonstrated most famously by the asteroid 99,942 Apophis in 2004. Apophis was discovered on the 19th of June, 2004, by astronomers Roy Tucker, David Tholen, and Fabrizio Bernardi at the Kitt Peak National Observatory in Arizona. Initial observations suggested the asteroid, which is roughly 370 meters in diameter, had a meaningful chance of striking Earth on the 13th of April, 2029. Over the following months, the impact probability rose as additional observations refined the orbit. On the 27th of December, 2004, almost exactly 20 years before the discovery of 2024 YR4, Apophis reached a Torino scale rating of 4, the highest ever assigned to any asteroid. At its peak, the estimated probability of a 2029 impact was approximately 2.7%. This triggered a wave of media coverage and public concern. But additional observations, including the recovery of pre-discovery images that extended the observational arc, allowed astronomers to refine the orbit further, and the probability dropped to 0 for the 2029 encounter. Apophis will make an extremely close approach to Earth on the 13th of April, 2029, passing within about 31,000 kilometers of the surface, closer than the orbit of many geostationary satellites, but it will not hit us. 2024 YR4 followed the same general pattern as Apophis, but with some critical differences that made it even more unsettling. The first difference was speed. Apophis was discovered in June of 2004, and the rising impact probability played out over a period of about 6 months before being resolved. 2024 YR4 compressed the entire drama into less than 2 months. It was discovered on the 27th of December, 2024. By the 29th of January, 2025, the International Asteroid Warning Network had issued a formal notification, and the Torino rating had reached 3. By the 18th of February, the probability had peaked at 3.1%. By the 23rd of February, it had dropped to effectively 0. 58 days from discovery to peak. 68 days from discovery to resolution. For the scientists involved, it was an incredibly compressed timeline. Every night of observation mattered. Every data point shifted the probability. Every cloudy sky at a key observatory represented lost information that might have resolved the threat sooner. The second difference was size. Apophis, at roughly 370 meters, is a civilization-threatening asteroid. An impact from Apophis would release energy equivalent to approximately 1,100 megatons of TNT, enough to devastate an area the size of a small country and trigger significant global climate effects. 2024 YR4, at roughly 60 meters, is a city killer, a very different category of threat, but one that is far more common and, in some ways, harder to defend against. Objects the size of Apophis are large enough to be detected at great distances, bright enough to be tracked for years, and well known enough that their orbits are mapped in detail. There are roughly 900 near-Earth asteroids larger than 1 kilometer in diameter, and we have found more than 95% of them. None of them is on a collision course with Earth for the foreseeable future. But objects the size of 2024 YR4 occupy a dangerous middle ground. They are large enough to cause catastrophic local damage, perhaps equivalent to a nuclear weapon detonating over a city, but small enough that they are incredibly difficult to detect. They are faint. They reflect little sunlight. They can approach Earth from blind spots in our observation network, and there are many more of them than there are of the larger asteroids. The estimated population of near-Earth objects in the 40 to 100 meter size range may number in the hundreds of thousands or even millions. We have found a tiny fraction. The third difference, and perhaps the most important, was the observational window. Apophis was discovered far from Earth and could be tracked for months and years, allowing a long observational arc that ultimately resolved the threat with high confidence. 2024 YR4 was different. It was discovered during a close approach, already moving away from Earth, and it was going to fade from view within a few months as it receded into the distance. The asteroid's orbital period is approximately 4 years. After its close approach in December 2024, it would not return to Earth's vicinity until late 2028. If the impact probability had not been resolved before the asteroid faded from view in April of 2025, the world would have faced an extraordinary and unprecedented situation. An asteroid with a 1 to 3% chance of hitting Earth would disappear into the darkness, unobservable and untrackable, for approximately 3.5 years, and for that entire period, the impact probability would remain frozen, unresolved, hanging over every calculation and every contingency plan. The European Space Agency explicitly acknowledged this possibility. Their Planetary Defense Office noted that if the asteroid faded from view with the impact probability still above 1%, it would remain on the risk list until 2028. This was not merely an academic concern. It had direct implications for decision-making. If the threat could not be resolved by observation alone, at what point would it become necessary to begin planning a response mission? At what probability threshold would the decision to launch a deflection spacecraft become justified? 1%? 5%? 10%? There is no established protocol for making this decision, and the cost of getting it wrong, in either direction, would be enormous. This brings us to the actual observations and the critical weeks of February 2025. On the 18th of February, the Sentry Automated Monitoring System at NASA's Jet Propulsion Laboratory calculated a 3.1% probability of Earth impact on the 22nd of December, 2032. This was based on a 55-day observation arc and represented the most refined orbital solution available at that time. The European Space Agency's Aegis system calculated 2.8%. These were consistent, independent estimates, converging on the same disturbing conclusion. The uncertainty region had contracted, and Earth was still inside it. 3.1%. If you had 100 lottery tickets and 3 of them were winners, you might feel that your odds were pretty good. You might even feel lucky. But if instead of a lottery prize, the winning ticket triggered an explosion, equivalent to 500 nuclear weapons over a populated area, the emotional calculus changes entirely. 3.1% is not a comfortable number when the stakes are measured in megatons and human lives. The Palermo scale rating for 2024 YR4 reached negative 0.18 on that same day. The Palermo scale is a logarithmic measure of asteroid risk that compares the probability and energy of a potential impact against the background risk, the statistical likelihood that a random, unknown asteroid of equal or greater size will strike Earth in the same time period. A Palermo rating of 0 means the asteroid's specific threat equals the background hazard. Positive values mean the specific threat exceeds the background. 2024 YR4 reached negative 0.18, meaning its threat was approximately 66% of the overall background hazard level. It was approaching, but had not quite reached, the level of danger that we statistically expect from random asteroid impacts over a comparable period. This may sound like good news, but it actually underscores a troubling reality. The background risk itself is not zero. We live beneath a constant, steady drizzle of cosmic threat, and 2024 YR4 came close to exceeding even that already non-zero baseline. And it gets worse. The impact risk corridor, the band of locations on Earth's surface where the asteroid might strike, was drawn along a line of low latitude, crossing the equator in multiple places. It began in the eastern Pacific Ocean off the coast of Colombia, ran through northern South America, crossed the equatorial Atlantic, passed through Nigeria, traversed Central Africa, cut through the northern edge of Eastern Africa, crossed the southwestern corner of the Arabian Peninsula, traversed the northwestern Indian Ocean, passed through southern India, and ended in Bangladesh. Along this corridor lived billions of people. Not millions, billions. Nigeria alone has a population exceeding 220 million. India's population exceeds 1.4 billion. Bangladesh has roughly 170 million people packed into an area smaller than the state of Iowa. If 2024 YR4 had struck any of the populated sections of this corridor, the casualties could have been staggering, not merely from the initial blast, but from the secondary effects, fires, infrastructure collapse, mass displacement, and the disruption of food, water, and medical systems across an enormous area. The asteroid was estimated at roughly 53 to 67 meters in diameter, based on infrared observations from the James Webb Space Telescope conducted in March of 2025. Earlier estimates, based on visible light brightness measurements, had placed the size range at 40 to 90 meters, but the infrared data narrowed this considerably. At the lower end of the range, around 53 meters, an impact would most likely produce an airburst, an explosion in the atmosphere at an altitude of several kilometers. An airburst of this magnitude would shatter windows and cause minor structural damage across a city-sized area. At the upper end, around 67 meters, the damage would be more severe, potentially collapsing residential buildings across a metropolitan area and shattering windows across a much larger region. Neither scenario involved a ground-level impact crater. At this size, stony asteroids typically explode in the atmosphere rather than reaching the surface. But the absence of a crater does not mean the absence of destruction. The Tunguska event produced no crater either, and it flattened 2,000 square kilometers of forest. But here is what makes this truly terrifying. The entire drama of 2024, YR4, played out in less than 2 months. From discovery on the 27th of December to peak probability on the 18th of February, 53 days. In 53 days, the world went from complete ignorance of this object's existence to the highest asteroid impact probability ever recorded in the history of astronomy. And then, almost as abruptly, it was over. On the evening of the 18th of February 2025, new observations came in from telescopes tracking the asteroid. The data was processed, the orbital solution was updated, and the probability dropped from 3.1% to 1.5% overnight. Then, over the following days, additional observations arrived from multiple facilities. Each new data point shrank the uncertainty region further. And this time, the region was shrinking away from Earth. By the 23rd of February, the probability had plummeted to 0.0017%. The Torino scale rating dropped from 3 to 0. The European Space Agency removed the asteroid from its risk list on the 25th of February. The International Asteroid Warning Network concluded its formal activities related to 2024 YR4. NASA removed the chance of a 2032 Earth impact on the 2nd of April, 2025, after accumulating a 91-day observation arc. The resolution of the threat also raised uncomfortable questions about public communication. How do you tell the public that there is a 3% chance of a nuclear-scale explosion over a populated area 7 years from now? How do you convey the nuance that this probability is expected to drop, that it almost certainly will drop, but that it might not? The media coverage of 2024 YR4 ranged from responsible to sensationalized. Some outlets reported the probability accurately and in context, emphasizing that the most likely outcome was a safe pass. Others led with apocalyptic headlines that exaggerated the danger and created unnecessary panic. The scientific community struggled with this communication challenge. Scientists are trained to speak in precise, qualified language. The public, understandably, wants clear, simple answers. Is it going to hit us? Yes or no? But the honest answer, for several weeks, was neither yes nor no. It was probably not, but we cannot be sure yet. That is a difficult message to deliver, especially when the consequences of the less likely outcome are measured in megatons. The communication challenge is not merely a public relations problem. It has direct implications for policy and decision-making. If the probability of impact had remained at 3% and the asteroid had faded from view, decision-makers in governments around the world would have faced an extraordinary dilemma. Do you begin evacuating cities along the impact corridor based on a 3% probability? Do you spend billions of dollars on a deflection mission when there is a 97% chance it is unnecessary? Do you keep the information classified to avoid panic, or do you share it transparently and risk economic disruption? These decisions involve trade-offs between different kinds of harm, and there is no established framework for making them. 2024 YR4 forced these questions into the open, even if only briefly, before the resolution of the threat allowed the world to return to more comfortable ground. The spectroscopic analysis of 2024 YR4 added an important dimension to the scientific understanding of the threat. Observations from the Gran Telescopio Canarias in the Canary Islands and the Lowell Discovery Telescope in Arizona suggested that the asteroid is most likely an S-type, a classification that indicates a stony composition rich in silicates and containing some nickel iron. S-type asteroids make up about 17% of the total asteroid population. This classification matters because composition affects how an asteroid behaves during atmospheric entry. Stony asteroids are more structurally cohesive than carbonaceous C-type asteroids, which tend to be weaker and more porous. A stony asteroid of 60 meters is more likely to penetrate deeper into the atmosphere before breaking up, delivering more of its energy closer to the ground. The Tunguska impactor, which is widely believed to have been a stony asteroid of similar composition, exploded at an altitude of only 5 to 10 kilometers, well within the troposphere. A more fragile body would have broken up higher, dispersing its energy over a larger volume of atmosphere and reducing the surface-level destruction. Researchers Carlos and Raúl de la Fuente Marcos published an analysis suggesting that 2024 YR4 may be related to a group of near-Earth asteroids on similar orbits, including objects designated 2017 UW 5 2018, GG4, 2019 SC, and 2020 MQ 61. All of these objects have orbits that cross Earth's path, and all have been flagged as virtual impactors at one time or another. The similarity of their orbits suggests they may share a common origin, perhaps fragments from a larger body that was disrupted at some point in the past. If this is the case, it implies that 2024 YR4 is not unique. There may be other, as yet undiscovered fragments on similar orbits, each one carrying the potential for a close encounter or collision. The 2015 Porangaba meteorite, a small meteor that fell in Brazil, has an orbit with a 5% probability of matching that of 2024 YR4, further supporting the possibility of a related family of objects. The close approach of 2024 YR4 would bring it within approximately 278,000 kilometers of Earth. That distance deserves some context. The Moon orbits Earth at an average distance of approximately 384,400 kilometers. 2024 YR4 will pass about 106,000 kilometers closer to us than the Moon. It will thread the gap between our planet and our nearest celestial companion. In the vastness of the solar system, where distances are typically measured in millions or billions of kilometers, a pass at 278,000 kilometers is extraordinarily close. It is equivalent to a bullet passing within a centimeter of your ear. You would feel the wind of its passage. You would hear the crack of its sonic boom, but you would be unharmed. Barely. The orbital mechanics of the close approach are intricate and revealing. 2024 YR4 follows an elliptical orbit around the Sun with a period of approximately 4 years, or 1,458 days. Its orbit is quite elongated, with an eccentricity of 0.656. This means the distance from the Sun varies enormously over the course of one orbit. At its closest point to the Sun, called perihelion, the asteroid passes within 0.87 astronomical units, slightly inside Earth's orbit. At its farthest point, called aphelion, it swings out to approximately 4.18 astronomical units from the Sun, well beyond the orbit of Mars and into the inner reaches of the main asteroid belt. This elongated orbit is the fingerprint of its violent history, evidence of the gravitational perturbations that flung it inward from the belt and set it on a collision course with the inner solar system. The asteroid's orbit is classified as Apollo type, meaning its semi-major axis is greater than 1 astronomical unit and its perihelion distance is less than Earth's aphelion distance. In simpler terms, it crosses Earth's orbit, not every 4 years, because the orbital planes are slightly inclined relative to each other and the timing of the crossings varies, but regularly enough that close encounters are inevitable over long periods. One of the most critical aspects of the 2024 YR4 story that is often overlooked is the role of what astronomers call precovery observations. A precovery is the identification of an asteroid in archival telescope images that were taken before the asteroid was officially discovered. If an image of 2024 YR4 could be found in data from years earlier, it would extend the observational arc backward in time, dramatically improving the orbital solution and potentially resolving the impact probability much sooner. The earliest known precovery observation of 2024 YR4 was from the same Atlas system, captured on the 25th of December, 2024, just 2 days before the official discovery. But this observation was of limited value because the asteroid was moving so fast and was so close to Earth that the measurement was imprecise. Far more valuable would be an observation from a previous close approach. The asteroid passed approximately 11.4 million kilometers from Earth on the 8th of September, 2016, and approximately 20.8 million kilometers on the 26th of October, 2020. If it could be found in images from either of these passages, it would extend the observational arc by 4 to 8 years, transforming the orbital solution from a short arc estimate to a long arc determination of far greater precision. A search through archival images from the Subaru telescope was conducted but did not locate the asteroid in the portion of the sky that was examined. However, researcher Sam Dean conducted a search of intermediate Palomar transient factory archives and may have located 2024 YR4 in data from 2016, which would extend the observation arc by approximately 3,067 days. If confirmed, this precovery would dramatically reduce the uncertainty in the asteroid's orbit and provide much tighter constraints on its future trajectory. This is the kind of painstaking archival detective work that rarely makes headlines but can be the difference between years of uncertainty and a prompt resolution of an impact threat. The mathematical machinery that underlies impact probability calculations is itself remarkable and worth understanding at a basic level. When astronomers observe an asteroid, they measure its position against the background stars at specific times. These measurements are called astrometric observations. Each observation has some degree of measurement error, a small uncertainty in the precise position. From these observations, orbital determination software computes the best fit orbit, the single trajectory that most closely matches all the observations. But because the observations have errors, there are many possible orbits that are nearly as consistent with the data as the best fit orbit. The software generates thousands of these alternative orbits, called clones or virtual asteroids, each one slightly different from the best fit but still consistent with the observations within their measurement uncertainties. Each virtual asteroid is then projected forward in time to the date of the potential impact. If a virtual asteroid's trajectory passes within 1 Earth radius of the center of our planet at the predicted time, it is counted as a virtual impactor. The impact probability is then estimated as the fraction of virtual asteroids that result in impacts, adjusted for the density of the probability distribution. If 1,000 virtual asteroids are generated, and 30 of them result in impacts, the estimated probability is roughly 3%. This is a simplification of a more sophisticated statistical process, but it captures the essential idea. The probability is not a measure of the asteroid's intent or behavior. It is a measure of our uncertainty. A 3% probability means that 3% of the trajectories consistent with our current observations lead to an Earth impact. As observations improve, and the range of consistent trajectories narrows, the probability will either converge towards 0, meaning no consistent trajectory leads to an impact, or toward 100%, meaning all consistent trajectories lead to an impact. In the case of 2024 YR4, it converged towards zero, but it took 58 days to reach the peak and 68 days to reach resolution. The behavior of the impact probability during those critical weeks followed a pattern that statisticians call Bayesian updating. Each new observation provided a piece of evidence, and the probability was updated to reflect all available evidence. But Bayesian updating is agnostic about the direction of the update. It tells you only that the probability should change. It does not tell you which way. For the scientists watching in real time, each update was a moment of tension. The data was processed. The orbit was recalculated, and the new probability appeared on their screens. Sometimes it went up, sometimes it went down, sometimes it barely moved. The emotional toll of this process, repeated night after night for nearly 2 months, should not be underestimated. These were not abstract numbers. They were measurements of the chance that millions of people might die, and the scientists performing the calculations carried the weight of that knowledge every single day. The observation campaign also involved one of the most challenging aspects of ground-based astronomy, the weather. Telescope observations require clear skies. Clouds, rain, wind, and even atmospheric turbulence can prevent observations or degrade their quality. During the critical weeks of January and February, the observing teams were at the mercy of weather conditions at telescope sites scattered across the globe. A single night of poor weather at a key observatory could delay the refinement of the orbital solution, prolonging the period of uncertainty and extending the public anxiety. The fact that enough clear nights occurred at enough sites to resolve the threat in time was, in part, a matter of meteorological fortune. In a future scenario, with different weather patterns, the resolution might not come as quickly. The question of how closely 2024 YR4 would actually pass by Earth was itself subject to refinement. The initial estimates of the closest approach distance on the 22nd of December 2032 had wide uncertainty bars. As observations accumulated, the best estimate converged on approximately 278,000 kilometers, with a 3 sigma uncertainty of about plus or minus 2,200 kilometers. This means that the actual distance could vary by a few thousand kilometers from the predicted value, but the range of possibilities was now narrow enough to exclude a collision. The asteroid will pass between Earth and the Moon, closer to us than our own natural satellite, but safely missing both. It is worth noting that the asteroid's close approach in 2032 will itself be a significant scientific event, regardless of the fact that the impact threat has been resolved. 2024 YR4 will pass closer to Earth than the Moon, offering telescopes an unusually close look at a small, fast-moving near-Earth object. The close approach will also provide a natural experiment in gravitational perturbation. The Earth-Moon system's gravity will significantly alter the asteroid's orbit during the encounter, and tracking these changes will provide valuable data about the asteroid's mass and density, properties that are difficult to measure remotely but critically important for assessing the effectiveness of potential deflection techniques. The close approach will also provide an opportunity to test and calibrate the next generation of asteroid tracking systems. By 2032, new facilities, like the Vera-C, Rubin Observatory should be fully operational, and space-based assets like NEO Surveyor may be in orbit. The 2032 flyby will serve as a real-world test of these systems' ability to track a fast-moving object at close range, a capability that will be essential for any future planetary defense scenario. The crisis was over, but it left behind a set of questions that remain unanswered. Questions about readiness, about infrastructure, about the gap between what we know and what we have built. These questions did not disappear with the probability, they sharpened. The story of 2024 YR4 did not end with the resolution of the Earth impact threat. What happened next added an entirely new dimension to the crisis, one that no one had fully anticipated, and that tested the planetary defense community in ways they had never been tested before. When the probability of an Earth impact dropped to effectively zero in late February of 2025, astronomers noticed something unexpected in the updated orbital calculations. The asteroid was no longer heading for Earth, but it was heading dangerously close to something else, the Moon. As the orbital solution was refined and the cloud of possible trajectories contracted. The paths that led to an Earth impact were eliminated one by one, but many of the remaining paths brought the asteroid perilously close to the lunar surface. By early March of 2025, calculations showed that 2024 YR4 had approximately a 4.3% chance of striking the Moon on the 22nd of December, 2032. The nominal closest approach to the Moon was calculated at roughly 22,900 kilometers from the center of the Moon, which translates to about 14,200 kilometers from the surface. The Moon is a sphere roughly 3,474 kilometers in diameter. The asteroid was projected to pass within a handful of lunar diameters of its surface. A lunar impact would have been an event without precedent in all of recorded human history. No human being has ever witnessed a significant impact on the Moon. The last major impact events on the Moon occurred billions of years ago, during the late heavy bombardment, a period of intense asteroid and comet impacts that shaped the Moon's cratered surface as we know it. A modern impact, observed in real time from Earth, would have been extraordinary, and the details of what would have happened are worth exploring in full. The impact, had it occurred, would have happened on the near side of the Moon, the hemisphere that perpetually faces Earth. This means the event would have been visible from our planet, at least to observers on the correct side of Earth at the right time. The crater produced by the impact would have been approximately 1 kilometer wide, or about 0.6 of a mile. To visualize this, imagine a circular pit, roughly the width of 10 football fields laid end to end, punched into the grey lunar soil. The surrounding area would have been showered with debris, creating a field of secondary craters and a bright ray system of ejected material that might have been visible through amateur telescopes for centuries. But the consequences would not have been limited to the Moon. When a high-velocity projectile strikes the lunar surface, it excavates a vast quantity of material and launches it into space. The Moon has no atmosphere to slow this debris, so the ejected material would have travelled outward at a range of velocities. Some would have been launched fast enough to escape the Moon's gravitational pull entirely. A fraction of that escaping debris would have been captured by Earth's gravity, potentially creating a brief but spectacular meteor shower visible from our planet in the days or weeks following the impact. The timing would depend on the exact geometry, and the predictions were highly uncertain, but the possibility was real enough that astronomers discussed it seriously. More concerning was the potential effect on satellites. Earth's orbital space is crowded with thousands of operational satellites, from communication and navigation satellites in geostationary orbit to scientific and military satellites in lower orbits. A shower of high-velocity lunar debris entering Earth's orbital space could have posed a collision risk to these satellites. The probability of any individual satellite being struck would have been extremely small, but the consequences of even a single collision with a critical satellite, such as a GPS navigation satellite or a military early warning satellite, could have been significant. The 4.3% lunar impact probability persisted stubbornly for months. Unlike the Earth impact probability, which was resolved relatively quickly in late February, the lunar impact probability proved resistant to refinement. The reason was simple geometry. The uncertainty region for the asteroid's position on the 22nd of December, 2032, was shaped like a long, narrow ellipse, stretched along the direction of the asteroid's orbital motion. Earth had been eliminated because the ellipse had moved to one side. But the Moon, being much smaller and positioned at a different angle relative to the uncertainty ellipse, remained within the range of possible paths. Eliminating the lunar impact required a much tighter constraint on the asteroid's exact position along its orbit, a constraint that required significantly more observational data. By the time 2024 YR4 faded from the view of ground-based telescopes in the spring and summer of 2025, the lunar impact probability had not been resolved. The asteroid was receding into the deep solar system, growing dimmer with each passing week, and even the world's most powerful ground-based telescopes could no longer detect it. The question of whether it might hit the Moon appeared destined to linger, unresolved, for years. Then, in February of 2026, something remarkable happened. NASA turned the most powerful space telescope ever constructed toward this tiny, ancient rock. The James Webb Space Telescope, a $10 billion infrared observatory positioned at the second Sun-Earth Lagrange point, approximately 1.5 million kilometers from Earth, was redirected from its primary mission of studying the earliest galaxies in the universe to observe a 60-meter asteroid in our own cosmic backyard. Observations were collected on the 18th and the 26th of February, 2026. The infrared data from Webb was processed by experts at NASA's Center for Near-Earth Object Studies at the Jet Propulsion Laboratory in Pasadena. The results were decisive. The new observations tightened the orbital solution sufficiently to rule out any chance of a lunar impact on the 22nd of December, 2032. 2024 YR4 would pass approximately 21,200 kilometers from the surface of the Moon, with an uncertainty of plus or minus 2,300 kilometers. Close, but not a collision. The crisis, both the Earth threat and the Moon threat, was finally, definitively over. The numbers are striking. It took the most expensive and most capable telescope ever built by humanity, an instrument designed to peer back in time to the birth of the first stars over 13 billion years ago, to determine that a rock smaller than a city block would not hit the Moon. This is the reality of planetary defense. It is not dramatic. It is not cinematic. It is painstaking, grinding, incremental work, dependent on the most advanced technology our species has ever created, applied to problems that are simultaneously mundane and existential. But the resolution of the 2024 YR4 threat should not be mistaken for evidence that the system works. It is better understood as evidence that the system got lucky. Because the story of this asteroid exposed a series of critical weaknesses in our planetary defense infrastructure, weaknesses that have not been fixed, and that could have catastrophic consequences when the next threatening asteroid appears. The first and most severe weakness is the sunward blind spot. 2024 YR4 approached Earth from the direction of the Sunday. No ground-based optical telescope can observe objects in this region of the sky. The glare of the sun overwhelms everything else, rendering this entire hemisphere effectively invisible to our detection systems. The asteroid was not detected until after it had already passed its closest point to Earth and moved into the night sky. This means that if 2024 YR4 had been on a direct collision course with Earth during its December 2024 close approach, we would have had no warning at all. None. Zero. The first indication of the impact would have been the flash of its atmospheric entry, followed within seconds by the shockwave. This is not a theoretical concern. It has already happened. On the 15th of February, 2013, an asteroid roughly 18 to 20 meters in diameter entered Earth's atmosphere above the city of Chelyabinsk in the Ural Mountains of Russia. The asteroid approached from the sunward direction. It was completely undetected by every telescope and every early warning system on the planet. No one saw it coming. The first anyone knew of its existence was a blinding flash in the morning sky, briefly brighter than the sun, followed by an enormous shockwave that arrived several minutes later. The shockwave blew out windows across 6 cities, damaged approximately 7,200 buildings, and sent roughly 1,500 people to hospitals and clinics with injuries. The majority of injuries were caused by flying glass from shattered windows. More than 180 people reported eye pain from the intense flash, and 70 reported temporary flash blindness. One woman suffered a broken spine and had to be airlifted to Moscow for treatment. The Chelyabinsk explosion released energy equivalent to approximately 440 to 500 kilotons of TNT. That is roughly 20 to 30 times the energy of the Hiroshima bomb. And the Chelyabinsk asteroid was only about 20 meters across, roughly 1/3 the diameter of 2024 YR4. Because the energy of an impact scales with the cube of the diameter and the square of the velocity, 2024 YR4 would have released energy at least 10 to 15 times greater than the Chelyabinsk event. We are talking about the difference between an explosion that breaks windows and one that collapses buildings. The sunward blind spot is a known problem with a known solution. The European Space Agency is developing a space-based infrared telescope called NEOMAR, which would be positioned at the first Sun-Earth Lagrange point, approximately 1.5 million kilometers from Earth on the sunward side. From this vantage point, NEOMA could detect asteroids approaching from the direction of the Sun by sensing their thermal emissions in infrared light, which are not drowned out by the Sun's visible glare. Simulations conducted by the ESA's Planetary Defense Office suggest that NEOMA would have detected 2024 YR4 approximately 1 month before ground-based telescopes did. 1 month of additional warning time, 1 month that could be the difference between orderly preparation and helpless surprise. Richard Moisel, the head of ESA's Planetary Defense Office, stated that simulations of NEOMA's performance in the 2024 YR4 scenario surprised even the development team, demonstrating that the telescope would have provided significantly earlier detection and a better initial size estimate. But NEOMA has not launched. It is still in development. And until it flies, the blind spot remains wide open, a gap in our defenses through which the next Chelyabinsk, or worse, could pass undetected. The second weakness is the gap in size coverage. The current generation of asteroid survey programs was designed primarily to find objects larger than 140 meters in diameter, the threshold above which an impact could cause catastrophic regional damage. NASA's stated goal, mandated by the United States Congress in 2005 through the George E. Brown Jr. Near-Earth Object Survey Act, is to find at least 90% of near-Earth objects 140 meters and larger. As of 2025, that goal had not been met. Approximately 60% of objects above this threshold had been catalogued. For objects in the 50 to 100 meter range, the size category that includes 2024 YR4, the detection rate is estimated at perhaps 5 to 10%. These smaller objects are fainter, harder to distinguish from background stars, and can approach much closer before becoming detectable. They are also far more numerous. Where there may be 25,000 near-Earth asteroids above 140 meters, there may be hundreds of thousands or millions in the 50 to 100 meter range. The third weakness is response time, and it is in many ways the most fundamental. Even if we detect a threatening asteroid with years of advance warning, our ability to actually deflect it remains largely theoretical. The most promising deflection technique, the kinetic impactor, was tested for the first time by NASA's Double Asteroid Redirection Test, the DART mission, on the 26th of September, 2022. DART was a spacecraft roughly the size of a large refrigerator that deliberately crashed into the asteroid moonlet Dimorphos, a small body approximately 160 meters in diameter that orbits a larger asteroid called Didymos. The impact was successful beyond expectations. Prior to DART's impact, Dimorphos orbited Didymos once every 11 hours and 55 minutes. After the impact, the orbital period decreased by approximately 33 minutes to 11 hours and 23 minutes. This was far more than the 7-minute change that would have been expected from a simple momentum transfer. The additional deflection came from the recoil effect of debris ejected from the impact site. The impact blasted material off the surface of Dimorphos, and the rocket-like thrust from that ejected material pushed the asteroid further than the spacecraft alone would have. The momentum enhancement factor was estimated at roughly 3.6, meaning the total momentum transferred to the asteroid was 3.6 times the momentum carried by the spacecraft itself. This was a landmark achievement. Humanity deliberately changed the orbit of a celestial body for the first time. The DART mission validated the kinetic impactor concept and proved that asteroid deflection is not merely theoretical. But DART was a test, conducted under ideal conditions, with years of planning, on a target whose orbit was already precisely known, with no time pressure and no real consequences for failure. In a genuine emergency, the situation would be radically different. Consider the timeline that 2024 YR4 presented. The asteroid was discovered in late December of 2024, with a potential impact date of December 2032. That appears to give roughly 8 years of warning, but the reality is far more constrained. The asteroid would fade from view by April of 2025 and would not be observable again until late 2028. If the impact probability had remained elevated, a deflection mission would have needed to be designed, built, launched, navigated to the asteroid, and executed, all within a window of perhaps 4 years from the asteroid's reappearance to the impact date. The DART mission took approximately 4 years from initial approval to impact, and that was a straightforward test with no urgency. A real deflection mission under crisis conditions, targeting a newly characterized asteroid with uncertain properties, would be vastly more complex. And there is a fourth weakness that underlies all the others. But here is the problem. We do not have a ready-to-launch deflection capability. There is no kinetic impactor spacecraft sitting in a clean room, fueled and waiting for a target. There is no rapid response launch vehicle dedicated to planetary defense. If a threatening asteroid were confirmed tomorrow, the earliest we could launch a mission would be measured in years, not months. The infrastructure does not exist. We have the science. We have the technology. We lack the hardware. The planetary defense community has studied several alternative deflection techniques, each with its own advantages and limitations. The gravity tractor concept involves a spacecraft flying in close formation with an asteroid for an extended period, using its own gravitational pull to slowly, almost imperceptibly, alter the asteroid's trajectory. This technique is elegant and requires no physical contact with the asteroid's surface, making it suitable for objects with unknown or fragile compositions. But it is extraordinarily slow. A gravity tractor mission to deflect an asteroid the size of 2024 YR4 might require years or even decades of continuous operation to produce a meaningful change in trajectory. For short warning scenarios, it is impractical. The ion beam deflection technique proposes firing a focused stream of ionized particles at an asteroid's surface, creating a gentle but persistent force that nudges the asteroid off course. This concept has been studied in laboratory settings and through computer simulations, but it has never been tested in space. The engineering challenges are significant, including the need for a spacecraft to maintain precise station keeping next to an irregularly shaped, rotating asteroid for extended periods while continuously directing a particle beam at its surface. For the most extreme scenarios, where warning time is very short and the asteroid is large, the only technique that could produce a meaningful deflection in weeks or months rather than years is a nuclear explosive device detonated near the asteroid's surface. The intense radiation from the explosion would vaporize a thin layer of the asteroid's surface material, creating a jet of expanding gas that would act like a rocket engine, pushing the asteroid in the opposite direction. Computer simulations suggest this technique could be highly effective, producing deflections many times larger than a kinetic impactor of equivalent mass. But the political, legal, and practical challenges are immense. The Outer Space Treaty of 1967 prohibits the placement of nuclear weapons in space, although there is ongoing debate about whether a planetary defense application would be permitted under the treaty's terms. There is also the risk that a nuclear detonation could fragment a weakly bound rubble pile asteroid into multiple large fragments, converting one problem into many problems, a scenario sometimes called the shotgun effect. Each of these techniques has been studied. None of them, with the single exception of the kinetic impactor demonstrated by DART, has been tested against a real asteroid. And even the kinetic impactor has been tested exactly once, on one type of asteroid, under controlled conditions. DART struck Dimorphos, which turned out to be a loosely bound rubble pile, a collection of boulders and gravel held together by weak gravitational and cohesive forces. The large momentum enhancement factor observed in the DART impact was likely a result of this rubble pile structure, which made it easier for the impact to excavate and eject large amounts of material. 2024 YR4, by contrast, appears to be a monolithic stony asteroid, a more cohesive body composed primarily of silicates and nickel iron. A kinetic impactor striking a monolithic target might produce a very different result, potentially a lower momentum enhancement factor and a smaller deflection. We simply do not know. The ESA's Hera mission, which launched in October of 2024, is scheduled to arrive at the Didymos Dimorphos system in late 2026. Hera will conduct detailed surveys of both asteroids, measuring the crater left by DART, precisely determining the mass of Dimorphos, and characterizing the physical changes caused by the impact. This data will be invaluable for understanding how kinetic impact works in practice and how it might be applied to future threats. But even with Hera's data, we will have validated the technique on exactly one asteroid, one target, one composition, one impact geometry. Extrapolating from this single data point to a confident, universal planetary defense strategy requires assumptions that we cannot yet verify. The fundamental lesson of 2024 YR4 is not that the system failed. The system performed its core function. It detected the asteroid, tracked it, calculated the probability, communicated the risk, and ultimately resolved the threat. But the system operated at the edge of its capabilities, with narrow margins, compressed timelines, and significant dependence on luck. The asteroid approached from a blind spot. It was discovered only after its closest approach. It nearly faded from view before the threat could be resolved, and if the probability had not dropped when it did, we would have faced years of uncertainty with no ready means of response. The timeline of 2024 YR4's probability evolution tells a story of its own, one worth examining in detail because it reveals how the machinery of planetary defense operates under pressure. On the 27th of December, 2024, the day of discovery, the initial impact probability was negligible, a tiny fraction of a percent. The orbital arc was only a few hours long, and the uncertainty region was vast. Over the next few weeks, as observations accumulated from multiple facilities, the probability began to climb. By mid-January, it had passed 1%. By the 29th of January, it reached approximately 1.2%, triggering the formal International Asteroid Warning Network notification. This was not a surprise to the scientific community. They had predicted that the probability would rise before it fell, but the public reaction was more visceral. Headlines blared about a potential asteroid impact. Social media amplified the concern, and the nuance that most experts expected the probability to ultimately reach zero was often lost in the noise. Through early February, the observations continued. The Very Large Telescope in Chile, one of the most powerful telescopes on Earth, was used to observe the asteroid as it grew fainter. Each observation sharpened the orbital solution slightly, but the probability continued to hover in the 1 to 2% range. The uncertainty ellipse was contracting, but it was contracting around a region that still included Earth. Every night, astronomers held their breath as the latest data was processed. Every morning they checked the updated probability figures on the Century and Aegis risk pages. Then came the 18th of February, 2025. The observation arc had reached 55 days. The orbital solution was the most precise it had ever been, and the probability peaked at 3.1% on the Century system, 3.1, the highest number ever displayed on that page for any asteroid in the system's history. For a few hours, 2024 YR4 held the dubious distinction of being the most dangerous known asteroid in the solar system. That evening, new observations arrived, the data was processed, and the probability dropped. It dropped to 1.5%. Then, over the next several days, more data arrived from telescopes around the world. The probability fell to 1%, then to 0.5%. Then, on the 23rd of February, it plummeted to 0.0017%. The uncertainty ellipse had finally contracted past Earth. The cloud of possible trajectories had narrowed to a region of space that no longer included our planet. The crisis was over. But the way the crisis ended is as instructive as the crisis itself. It ended because astronomers obtained enough observations to shrink the uncertainty region past Earth's position. This required clear skies, working telescopes, and access to some of the most powerful observational facilities on the planet. If any of those elements had been missing, the resolution would have been delayed. And if the delay had been long enough, if the asteroid had faded from view before the probability could be driven to zero, the world would have been left in limbo. This near miss of the informational kind, not the asteroid kind, is the detail that keeps planetary defense officials awake at night. The question of what we would do in a confirmed impact scenario remains largely unanswered in practical terms. There are plans, there are studies, There are white papers and conference proceedings and interagency memos, but there is no tested, rehearsed, end-to-end response capability. The DART mission demonstrated that we can hit an asteroid with a spacecraft, but DART targeted a 160-meter rubble pile at a known location with years of preparation. Deflecting a 60-meter monolithic stone on a compressed timeline is a very different challenge. The physics of kinetic impact depend critically on the target's properties. When DART struck Dimorphos, the impact excavated a large amount of material from the asteroid's surface. This ejected material, blasted outward by the collision, acted like rocket exhaust, pushing the asteroid further than the spacecraft's momentum alone would have. The momentum enhancement factor, designated by the Greek letter beta, was measured at approximately 3.6. This means that for every unit of momentum the spacecraft delivered, the asteroid received 3.6 units of momentum change. The extra 2.6 units came from the recoil of the debris. But this enhancement factor is not universal. It depends on the target's structure. A loosely bound rubble pile like Dimorphos is relatively easy to excavate. The material is weakly held together, and the impact sends large volumes of debris flying. A monolithic body like 2024 YR4 would be much harder to excavate. The material is more cohesive, more tightly bound. Less debris would be ejected, and the momentum enhancement factor would likely be lower. How much lower? We do not know. It could be 2. It could be 1.5. It could be close to 1, meaning the spacecraft's own momentum would be nearly the only force acting on the asteroid. Without additional tests on different types of asteroids, we are guessing, and guessing is not a comfortable basis for planetary defense. And the Vera C. Rubin Observatory, currently being commissioned in Chile, represents a potential leap forward in near-Earth object detection. The Rubin Observatory is equipped with an 8.4-meter mirror and a 3.2 billion pixel camera, making it the most powerful survey telescope ever built. When it begins its legacy survey of space and time, it will scan the entire visible sky every few nights, detecting objects far fainter than current surveys can reach. The Rubin Observatory is expected to dramatically increase the rate of near-Earth object discovery, potentially finding tens of thousands of previously unknown objects in its first few years of operation. Many of these will be in the 50 to 100 meter size range that includes 2024 YR4. For the first time, we will begin to build a comprehensive census of the city killer population. But the Rubin Observatory, powerful as it is still a ground-based telescope. It can only observe the night sky. It cannot see asteroids approaching from the sunward direction. And it will generate such an enormous volume of data, roughly 20 terabytes per night, that the computational challenge of processing and analyzing the observations in real time is itself a significant hurdle. The software systems needed to automatically identify new near-Earth objects from this flood of data are still being developed and refined. The need for a space-based detection system positioned between Earth and the Sun is widely recognized in the planetary defense community. NASA's Near-Earth Object Surveyor mission, commonly called NEO-Surveyor, is an infrared space telescope designed to be placed in orbit around the Sun at the first Earth-Sun Lagrange point. From this position, it would survey the infrared sky for the thermal signatures of asteroids, including those approaching from the sunward direction. NEO-Surveyor is expected to find approximately 65% of near-Earth objects larger than 140 meters within its first 5 years of operation. And it would also be capable of detecting many smaller objects, including those in the size range of 2024 YR4. However, NEO-Surveyor has faced delays and funding challenges, and as of 2025, its launch was not expected until the late 2020s at the earliest. The gap between what we need and what we have is not a matter of technology. The technology exists, the telescopes can be built, the spacecraft can be designed and launched, the computer algorithms can be written. What is missing is the sustained political will and financial commitment to make it happen at the pace the threat demands. Every year that passes, without a comprehensive detection network, is a year during which a 2024 4-class asteroid could arrive undetected and strike without warning. That is not readiness. That is, there is a subtle but important distinction between the concept of a confirmed impact and a probable impact that bears examination. In the case of 2024 YR4, the impact was never confirmed. The probability was always a measure of uncertainty. At its peak, there was a 96.9% chance that the asteroid would miss Earth. That is overwhelmingly likely. But the 3.1% chance of an impact was not negligible, and the consequences of that 3.1% were so severe that the situation demanded the full attention of the planetary defense community. In a future scenario, the probability might climb higher. It might reach 10%, or 20%, or 50%. At what point does a probable impact become a de facto confirmed impact for purposes of decision-making? There is no agreed-upon threshold. Some analysts argue that any probability above 1% should trigger active preparation, including the preliminary design of a deflection mission. Others argue that the threshold should be higher, perhaps 10%, to avoid the costs and disruptions of responding to false alarms. The debate is unresolved, and 2024 YR4 did not resolve it, because the probability dropped before the question became urgent. But the question will come up again, and next time, the probability may not cooperate by dropping in time. There is also the question of what happens during the years of uncertainty, the gap between detection and resolution. 2024 YR4 was resolved in less than 2 months. But a future asteroid might present a scenario in which the probability remains elevated for years. Imagine an asteroid discovered with a 2% chance of impact a decade in the future. 2% is low enough that a deflection mission might seem premature, but 2% is high enough that ignoring the threat would be irresponsible. What do you do? Do you begin designing a spacecraft just in case? Do you alert the public? Do you start identifying evacuation routes for cities along the impact corridor? These decisions have enormous political, economic, and social consequences, and there is no playbook for making them. The absence of such a playbook is itself a form of risk. It means that when the next 2024 YR4 arrives, and when the probability does not conveniently drop to zero, the world's response will be improvised. Improvisation is not a strategy. It is the absence of one. That is not readiness. That is survival by the narrowest of margins. There is a deeper truth buried within the story of 2024 YR4, and it is one that extends far beyond the specifics of this particular asteroid. Beyond the orbital calculations and the probability estimates and the telescope observations, the deeper truth is this. We live on a small, fragile world that is moving through a vast and indifferent cosmos, and the only thing standing between us and a devastating impact is a patchwork of telescopes, a handful of computer algorithms, and a small community of dedicated scientists who are working with a fraction of the resources they need. That is it. That is the entire planetary defense infrastructure of the human species. A few hundred people, a few dozen telescopes, and a budget that would not cover the cost of a single modern naval destroyer. Let that sink in. The total global budget for planetary defense, including asteroid detection, tracking, characterization, and deflection research, is measured in the tens of millions of dollars per year, not billions. Not hundreds of millions, tens of millions. NASA's Planetary Defense Coordination Office, the single most important institution in the world for protecting our planet from asteroid impacts, operates on a budget that represents a tiny sliver of NASA's total spending, which itself is less than 1% of the United States federal budget. The European Space Agency's Planetary Defense Office is similarly constrained. The combined global spending on planetary defense is roughly comparable to the cost of producing a single Hollywood blockbuster film about asteroid impacts. We spend more on fictional asteroids than on real ones. To put this in even sharper perspective, consider some comparisons. The cost of a single F-35 Joint Strike Fighter aircraft is approximately $80 million. That is roughly equivalent to the entire annual operating budget of NASA's Near-Earth Object Observations program. The United States military spends more money in a single day than the entire world spends on planetary defense in a year. The global cosmetics industry generates revenue of approximately $380 billion per year. The global spending on Halloween candy in the United States alone exceeds $2.6 billion annually. The entire budget for finding and tracking every asteroid that could destroy a city, a region, or a civilization is a rounding error in any of these figures. This is not science fiction. This is the world we live in. This is the arithmetic of our priorities, laid bare. Consider what we know about the population of near-Earth objects. Astronomers estimate that there are roughly 25,000 near-Earth asteroids larger than 140 meters in diameter. These are the ones capable of regional devastation, impacts that could destroy an area the size of a small country and cause hundreds of thousands or millions of casualties. As of 2025, approximately 15,000 of these had been found. That leaves roughly 10,000 still lurking in unknown orbits, each one a potential catastrophe waiting to be discovered. Below 140 meters, the population grows steeply. There may be hundreds of thousands of objects in the 50 to 100 meter range, the city killer class that includes 2024 YR4. We have found a tiny fraction of them. Perhaps 5%, perhaps less. The frequency of impacts from objects in this size range, roughly 50 to 70 meters, is estimated at once every several hundred to a few thousand years. A Tunguska-class event, once every few centuries to a few millennia, that might sound reassuringly rare, but it is a statistical average, not a schedule. Impacts do not follow a calendar. They are random events governed by the chaotic dynamics of orbital mechanics. The last Tunguska-scale event was in 1908. The next one could happen tomorrow. It could happen next year. It could happen in 3,000 years. We have no way of knowing. The probability of such an impact in any given year is small, roughly 1 in 500 to 1 in a few thousand. But the probability of such an impact within the lifetime of a person alive today is not negligible. Over the course of a century, the cumulative probability becomes significant, and over the course of a millennium it approaches certainty. We are, in the most literal statistical sense, overdue for a reckoning. Not necessarily from 2024 YR4, not from any specific rock, but from the simple, relentless mathematics of probability applied to a shooting gallery that never stops. Let that sink in. The Chelyabinsk event of 2013 should have been a permanent wake-up call. It was not. An asteroid entered Earth's atmosphere without any warning whatsoever. It exploded above a city of more than 1 million people with the force of roughly 30 Hiroshima bombs. It injured more than 1,500 people. It damaged over 7,000 buildings. The shockwave was powerful enough to knock people off their feet and blow doors off their hinges. And the only reason it was not a mass casualty event, the only reason the death toll was not measured in thousands or tens of thousands, was a combination of factors that amounted to luck. The asteroid entered at a shallow angle, spreading its energy over a longer path through the atmosphere. It was small enough that most of its energy was deposited high up, at an altitude of roughly 30 kilometers, far enough from the ground that the blast wave was attenuated before reaching the surface. And Chelyabinsk, while a city of over 1 million people, is a relatively low-density urban area compared to the megacities of Asia and South America. If the same asteroid had entered the atmosphere at a steeper angle, or if it had been larger by a factor of 2 or 3, or if it had arrived above Lagos or Mumbai or Dhaka instead of Chelyabinsk, the outcome would have been catastrophically different. Something is deeply wrong with our assumptions about the priority of this threat. 2024 YR4 illustrated this with crystalline clarity. The scientific community responded to the threat with impressive speed and admirable coordination. Telescopes around the world redirected their observations. International warning networks activated. The United Nations endorsed response groups convened meetings. Press releases were issued. The public was informed. But behind this competent response was a sobering reality. The response depended entirely on a small number of facilities and a small number of individuals. If weather had prevented observations at critical moments, if a key telescope had been offline for maintenance, If the asteroid had been slightly fainter and slipped below the detection threshold of the available instruments, the outcome could have been very different. Not the outcome for Earth, the asteroid would still have missed, but the outcome for our knowledge. We might not have known it would miss until much later, or at all. The story of 2024 YR4 also revealed something profound about the nature of cosmic risk and how poorly human institutions handle it. The impact risk corridor passed through some of the most densely populated and economically vulnerable regions on Earth: Colombia, Nigeria, India, Bangladesh. These are countries with enormous populations, limited infrastructure for mass evacuation, and minimal capacity to absorb the kind of catastrophic shock that a 7.7 megaton explosion would deliver. If the probability had remained elevated and a deflection mission had been deemed necessary, who would have paid for it? Who would have launched it? Who would have decided which deflection technique to use? And if the deflection attempt had failed, or worse, if it had succeeded but redirected the asteroid toward a different populated area, who would have been responsible for the consequences? These questions have no established answers. The international governance framework for planetary defense is incomplete at best and non-existent at worst. There is no treaty that assigns responsibility for asteroid deflection. There is no international fund to pay for emergency missions. There is no established protocol for deciding when to act and when to wait, or for determining who bears the costs and risks of a deflection attempt. The International Asteroid Warning Network provides coordination and recommendations, but it has no authority to command action. The Space Mission Planning Advisory Group provides technical advice, but it cannot compel any nation to launch a spacecraft. If an asteroid were heading for Earth and two nations disagreed about the appropriate response, there is no mechanism for resolving that disagreement. If a deflection attempt were proposed that would shift the impact point from one country to another, there is no legal framework for adjudicating the resulting conflict. The deeper truth is that 2024 YR4 was a rehearsal, an unplanned, unscripted rehearsal for a scenario that will, with mathematical certainty, eventually occur for real. An asteroid will be discovered on a genuine collision course with Earth. It may be larger than 2024 YR4. It may be on a shorter timeline. It may approach from the sunward blind spot, giving even less warning. And when that day comes, the decisions made in the first weeks and months will determine the outcome for millions, potentially billions of people. The Yarkovsky effect adds another layer of complexity to this already challenging picture. This subtle force, named after the Russian civil engineer Ivan Osipovich Yarkovsky, who first proposed it in the late 1800s, arises from the uneven thermal radiation emitted by a rotating asteroid. As the asteroid absorbs sunlight on its sun-facing side and re-radiates that energy as heat, the asymmetric emission creates a tiny but persistent thrust. For 2024 YR4, which rotates in a retrograde direction, the Yarkovsky effect acts as a gentle brake on the asteroid's orbital motion, causing its orbit to slowly shrink over time. This drift is minuscule, far too small to measure directly from ground-based observations over short time periods. But over centuries and millennia, it accumulates, subtly shifting the asteroid's orbital parameters and making long-term trajectory predictions increasingly uncertain. This means that predicting 2024 YR4's future path requires not just precise knowledge of its current position and velocity, but also a detailed understanding of its physical properties, its size, shape, mass, spin rate, spin axis orientation, thermal conductivity, and surface reflectivity. Each of these parameters influences the Yarkovsky effect, and the Yarkovsky effect influences the orbit. It is a cascade of uncertainties, each one amplifying the next. The close encounter with the Earth-Moon system in 2032 will dramatically amplify all existing uncertainties in 2024 YR4's orbit. Even though the asteroid will miss both Earth and the Moon, it will pass close enough to both that their gravitational pull will significantly perturb its trajectory. After 2032, the asteroid's orbit becomes very difficult to predict. The uncertainty in its position grows rapidly with time. By the mid-2040s, the uncertainty spans billions of kilometers. By the year 2123, The 3 sigma uncertainty in the asteroid's position exceeds 4 astronomical units, or roughly 600 million kilometers. We simply do not know where this rock will be a century from now, and we cannot rule out future close encounters or potential impacts without continuous, long-term monitoring. This is the fundamental challenge of planetary defense compressed into a single example. The universe is not static. Orbits evolve. Gravitational encounters change trajectories. Tiny thermal effects accumulate over long periods. And we are trying to predict the behavior of millions of small, dark, tumbling rocks in a vast dynamic system using a limited number of telescopes and a finite amount of time. It is a staggering challenge. And the stakes, measured in cities and lives and the continuity of civilization, could not be higher. There is a concept in risk analysis called the expected value of a catastrophe. It is calculated by multiplying the probability of the event by the magnitude of the damage. For 2024 YR4, at its peak probability of 3.1%, the expected value calculation was staggering. If the potential damage of an impact were estimated at, say, $100 billion in direct costs and an unquantifiable cost in human lives, then the expected value of the damage was roughly $3 billion. $3 billion in expected damage from a single asteroid with a 3% chance of impact. Against this expected cost, the total global spending on planetary defense was perhaps $100 million per year. The ratio of expected damage to prevention spending was roughly 30-1. In any other domain of risk management, from insurance to public health to military planning, such a disparity would be considered grossly irresponsible. And the expected value calculation for 2024 YR4 was for a city killer, not a civilization ender. The expected value of damage from the entire population of undetected near-Earth asteroids, including those large enough to cause regional or global catastrophe, is far higher. Various studies have estimated the annualized expected damage from asteroid impacts at between $100 million and several billion dollars per year, depending on assumptions about the undetected population and the economic modeling of impact consequences. Even the most conservative estimates suggest that we are dramatically underspending on planetary defense relative to the risk. The question of why we underspend is itself instructive. It is not because the science is uncertain. The science is quite clear. Asteroids hit Earth. They will continue to hit Earth. Some of them will cause enormous damage. These are not predictions. They are statements of physical law, supported by a geological record spanning billions of years. The reason we underspend is psychological. We suffer from what risk analysts call the availability bias. We overweight risks that are vivid, recent, and easily imagined, and we underweight risks that are abstract, infrequent, and hard to visualize. A car accident is vivid. A plane crash is vivid. A terrorist attack is vivid. An asteroid impact, something that has never happened within the lifetime of any person alive today, on a scale large enough to cause mass casualties, is not vivid. It is theoretical. It is statistical. And statistical threats, no matter how real, struggle to compete for attention and resources with vivid ones. Consider what the world looked like on the night of the 18th of February, 2025, when the probability peaked. Somewhere in a control room at the Jet Propulsion Laboratory, a computer screen displayed the number 3.1%. A number derived from thousands of virtual asteroid trajectories, each one a possible future path of a 60-meter rock through the inner solar system. 3 out of every 100 of those simulated futures ended with a flash over the equatorial belt. 3 out of every 100 ended with a shockwave rippling outward across a landscape that, depending on the exact point of impact, might have been Pacific Ocean or Colombian rainforest or Nigerian savanna or Indian farmland. The scientists who read that number understood its context. They understood that the most likely outcome, by far, was a safe pass. They understood that the probability was expected to decline with additional observations. They had seen this pattern before with Apophis and with numerous other asteroids that briefly appeared on the risk list before being cleared, but understanding the statistics does not eliminate the emotional weight of the numbers. When you calculate a probability that involves millions of human lives, the mathematics takes on a gravity that pure theory cannot convey. This is the burden that planetary defense scientists carry, often in obscurity, without recognition, and without the resources they have been requesting for decades. They are the sentinels at the edge of civilization, watching the sky for dangers that most people prefer not to think about. When an asteroid like 2024 YR4 appears, their work becomes briefly visible. The world pays attention for a few weeks, asks a few questions, expresses a few concerns, and then moves on. The scientists remain at their stations, watching, calculating, waiting for the next alert. The economic argument for planetary defense, when examined rationally, is overwhelming. The cost of a comprehensive planetary defense program, including expanded survey telescopes, space-based detection systems, standing deflection capability, and international coordination infrastructure, has been estimated at roughly $2 to $5 billion over a decade. That is the cost of a single large skyscraper, or a few weeks of operation for the United States military, or roughly 1% of what the world spends annually on advertising. In exchange for this investment, we would dramatically reduce the risk of a catastrophe that could kill millions of people, destroy trillions of dollars in infrastructure, and destabilize the global economy. The expected return on investment, calculated by multiplying the probability of impact by the cost of the damage and dividing by the cost of prevention, is astronomically favorable. There are very few investments in the entire portfolio of human activity that offer a better ratio of cost to expected benefit. And yet the money has not been committed. The telescopes have not been built at the pace needed. The spacecraft have not been constructed. The governance frameworks have not been established. The reason is not rational. It is psychological. Human beings are spectacularly bad at processing low probability, high consequence risks. We systematically underweight events that have never happened to us personally, even when the evidence for their eventual occurrence is overwhelming. We are wired by evolution to focus on immediate threats we can see and feel and react to in real time. An asteroid that might arrive in 50 years or 500 years does not trigger the same urgency as a predator in the bushes or arrival at the gates. Our cognitive architecture is optimized for survival on the African savanna, not for planetary defense on a cosmic timescale. And this mismatch between the threat we face and the psychology we bring to it is perhaps the most dangerous vulnerability of all. 2024 YR4's origin tells its own story about the deep history of the solar system and the restless motion of its smallest inhabitants. The asteroid originated in the central main asteroid belt, the region between approximately 2.2 and 2.8 astronomical units from the Sunday. This is a zone dominated by S-type and C-type asteroids, the stony and carbonaceous remnants of the protoplanetary disk from which the planets formed. Over time, gravitational interactions with Jupiter, particularly at orbital resonances like the 3-to-1 mean motion resonance at 2.5 astronomical units, perturbed the asteroid's orbit, increasing its eccentricity and sending it on an increasingly elongated path that eventually crossed the orbits of the inner planets. The inward migration was not smooth or gradual. It was chaotic, marked by sudden jumps in orbital parameters as the asteroid crossed through multiple resonances. The asteroid's retrograde rotation, spinning in the opposite direction to its orbital motion around the Sun, indicates that the Yarkovsky effect has been acting as a slow but persistent force, shrinking the orbit over time and contributing to its inward drift. This process, from stable mainbelt resident to Earth-crossing near-Earth object, likely took millions of years. And it is a process that is still ongoing, for thousands of other asteroids currently being nudged inward by the same gravitational forces. The astronomical community's response to 2024 YR4 also highlighted a growing tension between the traditional rhythms of scientific research and the urgent demands of planetary defense. Telescope time at major observatories is a precious and heavily competed resource. Astronomers submit proposals months or even years in advance, and allocation committees decide which programs receive time based on scientific merit, feasibility, and priority. When 2024 YR4 was flagged as a potential threat, Urgent requests for telescope time were submitted under special discretionary programs that allow observatory directors to override the normal allocation process in exceptional circumstances. This mechanism worked in the case of 2024 YR4, but it is an improvised solution, not a systematic one. The Gemini South Telescope in Chile, for example, was used to observe 2024 YR4 under director's discretionary time, a special allocation reserved for urgent scientific opportunities. The observations were invaluable, providing the multi-wavelength photometric data needed to constrain the asteroid's composition, shape, and rotation state. But the fact that obtaining these observations required invoking emergency procedures at one of the world's premier observatories illustrates the fragility of the system. If multiple asteroid threats were to emerge simultaneously, or if a threat emerged during a period of high demand for telescope time from other scientific programs, the capacity to respond could be severely strained. The experience also demonstrated the value of international cooperation in planetary defense. Observations of 2024 YR4 were contributed by telescopes in Chile, Hawaii, the Canary Islands, Arizona, New Mexico, and elsewhere. The data was shared rapidly through established channels, including the Minor Planet Center at the Smithsonian Astrophysical Observatory in Cambridge, Massachusetts, which serves as the international clearinghouse for asteroid observations. This cooperation was largely informal, built on personal relationships, institutional goodwill, and a shared sense of urgency. It worked, but informal cooperation is not a substitute for systematic infrastructure. The next asteroid threat may not afford the luxury of relying on goodwill and improvisation. The discovery of 2024 YR4 also underscored a fundamental limitation of our current approach to planetary defense. We are reactive, not proactive. We wait for asteroids to come to us, appearing in our telescopes during close approaches, rather than going out to find them. A truly comprehensive planetary defense program would include not just ground-based and space-based telescopes, but also spacecraft missions to survey the near-Earth object population directly, visiting and characterizing the most potentially hazardous objects to determine their sizes, compositions, and structural properties. Knowing that an asteroid is 60 meters across and stony, rather than 100 meters across and carbonaceous, could make the difference between an effective deflection strategy and a failed one. But such missions are expensive, and the funding has not been forthcoming. The OSIRIS-REx mission, which collected a sample from the asteroid Bennu in 2020 and returned it to Earth in September of 2023, demonstrated the scientific value of direct asteroid encounters. Bennu is a potentially hazardous asteroid roughly 500 meters in diameter, and the detailed characterization provided by OSIRIS-REx transformed our understanding of its physical properties. But Bennu was selected for scientific reasons, not for planetary defense. A dedicated program of reconnaissance missions to the most dangerous near-Earth objects, one that would systematically characterize the objects we might one day need to deflect, does not yet exist. So what does all of this mean? What does the story of 2024 YR4 tell us about our place in the cosmos, about the choices we need to make as a species, and about the future that awaits us if we choose to act or to remain passive? The first and most immediate implication is humility. Deep, bone-level humility. We live on a thin skin of rock and water wrapped around a ball of molten iron, orbiting an average star in the outer reaches of an unremarkable spiral galaxy, and we are surrounded by objects that could end our civilization with a single collision. We have known this intellectually for decades. The crater record on the Moon, visible through any modest telescope, is a permanent reminder that impacts are not rare events in the solar system, but commonplace ones. The extinction of the dinosaurs 66 million years ago, caused by an asteroid roughly 10 kilometers in diameter that struck what is now the Yucatan Peninsula, demonstrated that cosmic impacts can reshape the entire biosphere. The Tunguska event of 1908 showed that even modest-sized asteroids can produce devastation on a scale comparable to nuclear weapons. The Chelyabinsk event of 2013 proved that such events can happen without warning above populated areas in the modern era. And yet, despite all of this evidence, we continue to treat asteroid impact as a remote, abstract, almost theoretical risk. We acknowledge it in policy documents and conference presentations and the occasional newspaper headline, and then we return to our daily routines without committing the resources necessary to address it. 2024 YR4 briefly pierced this complacency. For a few weeks, in January and February of 2025, the threat felt real. It had a name. It had a probability. It had a map showing which cities lay beneath its potential path. And then the probability dropped, and the complacency returned. The second implication is urgency. The gap between our knowledge of the threat and our readiness to address it is wide and dangerous, and growing wider with each year that passes without meaningful investment. We know that near-Earth asteroids in the 50 to 100 meter range can devastate cities. We know that we have catalogued perhaps 5 to 10% of these objects. We know that our detection systems have a critical blind spot in the sunward direction that renders approximately half the sky invisible at any given time. We know that we do not have a deflection spacecraft ready to launch on short notice. We know that the international governance framework for planetary defense is incomplete. Each of these problems has a solution. Space-based telescopes like NEOMER can fill the sunward blind spot. Next-generation survey telescopes like the Vera C. Rubin Observatory can dramatically accelerate the rate of asteroid discovery. Stockpiled kinetic impactors or rapid response spacecraft can provide a standing deflection capability. International treaties and protocols can establish clear decision-making authority and funding mechanisms for emergency response. None of these solutions is beyond our technological or economic capability. All of them are within reach. What is lacking is not the ability to act, but the will. If the sun were a basketball, the Earth would be a small pea sitting about 26 meters away. And 2024 YR4 would be an invisible, undetectable particle of dust somewhere in the surrounding air, too small to see, too small to feel, carrying enough energy to reshape the surface of the pea. This is our situation. We are a pea in a dusty room, and we have barely begun to map the dust. The third implication is philosophical, and it runs deeper than budgets or policy decisions. 2024 YR4 forced us to confront, however briefly, the possibility that our future is not guaranteed. We tend to live as though the ground beneath our feet is permanent, as though the sky above us is safe, as though tomorrow is certain. But the cosmos offers no such assurances. The same gravitational forces that hold us in orbit around the sun also direct rocks toward our planet. The same laws of physics that allow us to build cities and launch spacecraft also allow chunks of primordial stone to carry the energy of thermonuclear weapons across billions of kilometers of empty space. We exist in a universe that is magnificent and beautiful and utterly, completely indifferent to our survival. There is something clarifying about confronting this reality, something that strips away the noise of daily life and forces us to focus on what matters. If our existence can be ended by a tumbling piece of rock that nobody saw coming, then what are we doing with the time we have? Are we spending our collective resources wisely? Are we cooperating as effectively as the threat demands? Consider for a moment the emotional geography of this story. On the 27th of December, 2024, a small team of astronomers at a telescope in Chile captured 4 images that contained a faint streak of light. Within days, automated algorithms had flagged the object as potentially hazardous. Within weeks, the probability had climbed above 1%, and headlines around the world announced that a city-killer asteroid had Earth in its sights. Across the impact risk corridor, from Colombia to Bangladesh, billions of people went about their daily lives largely unaware of the calculations being performed in laboratories and observatories on their behalf. The farmers in the Nigerian countryside, the school children in Indian cities, the fishermen in the coastal waters of Bangladesh, all of them living beneath the narrow band where the asteroid might, with a probability of 3 in 100, deliver an explosion equivalent to hundreds of nuclear weapons. And then the probability dropped, and the story faded from the news cycle, replaced by the next crisis and the next headline, but the asteroid did not disappear. It is still there, orbiting the sun, following the same path it has followed for billions of years, and there are others like it, many others, most of them undetected, most of them unnamed. most of them following orbits that cross Earth's path at regular intervals, each one a potential Tunguska, each one a potential Chelyabinsk, each one a potential catastrophe waiting for the geometry to align. Are we thinking on timescales long enough to matter, not just the next election cycle or the next fiscal quarter, but the next century and the next millennium? The paradox at the heart of planetary defense is this: if the system works perfectly, nothing visible happens. If every threatening asteroid is found, tracked, and deflected, the result is indistinguishable from a universe where no asteroids ever threatened us at all. Success is invisible. And invisible success is extraordinarily difficult to fund, to justify, to sustain. We are wired to respond to disasters after they happen, not to prevent them before they occur. We build levees after the flood, not before. We stockpile medicine after the pandemic, not before. And we will invest seriously in planetary defense only after an impact, not before. The question is whether that belated investment will come in time to prevent the next one, or whether the next one will come before we are ready. Every few centuries, on average, an object the size of 2024 YR4 enters our atmosphere. Every few millennia, one of these objects strikes a populated area. Every few 100,000 years, an object large enough to cause civilizational disruption arrives, and every few tens of millions of years, an extinction-level impactor strikes. These are statistical frequencies, averages over geological time. They do not tell us when the next impact will occur. They tell us only that it will occur. The universe is patient. It has all the time in the world, and it does not wait for us to be ready. We are also confronting a challenge of institutional memory. The Tunguska event occurred more than a century ago. The scientists who studied it are long dead. The witnesses are long dead. The event lives only in written records and in the faint imprint it left on the Siberian landscape, now largely recovered by forest regrowth. The Chelyabinsk event of 2013, while well documented by video and scientific instruments, has already begun to fade from public consciousness. In another decade, it will be a footnote. In another century, it will be forgotten by all but specialists, and the urgency that these events briefly generated will fade with the memory of them. This is the cycle that planetary defense advocates fight against. An event occurs, attention spikes, funding increases modestly, then the attention fades, the funding plateaus or declines, and the preparations stall until the next event. And the next event could be far worse than Chelyabinsk, far worse than Tunguska. The next event could arrive without warning from the sunward blind spot, targeting a megacity of 20 million people. And if it does, the conversation about planetary defense will shift overnight from should we to why did we not. But by then, it will be too late for the people beneath the blast. Consider for a moment the emotional geography of this story. On the 27th of December, 2024, a small team of astronomers at a telescope in Chile captured 4 images that contained a faint streak of light. Within days, automated algorithms had flagged the object as potentially hazardous. Within weeks, the probability had climbed above 1%, and headlines around the world announced that a city-killer asteroid had Earth in its sights. Across the impact risk corridor, from Colombia to Bangladesh, billions of people went about their daily lives largely unaware of the calculations being performed in laboratories and observatories on their behalf. The farmers in the Nigerian countryside, the school children in Indian cities, the fishermen in the coastal waters of Bangladesh, all of them living beneath the narrow band where the asteroid might, with a probability of 3 in 100, deliver an explosion equivalent to hundreds of nuclear weapons. And then the probability dropped, and the story faded from the news cycle, replaced by the next crisis and the next headline. But the asteroid did not disappear. It is still there, orbiting the Sun, following the same path it has followed for billions of years, and there are others like it, many others, most of them undetected, most of them unnamed. Most of them following orbits that cross Earth's path at regular intervals, each one a potential Tunguska, each one a potential Chelyabinsk, each one a potential catastrophe waiting for the geometry to align. There is an ancient human impulse to look at the sky and see safety. The sky has always been the realm of constancy. The same stars rise and set each night. The same moon waxes and wanes each month. The same sun crosses the same arc each day. For thousands of years, the sky was humanity's most reliable clock, its most dependable calendar, its most enduring source of predictability and order. The discovery that the sky also contains danger, that it is not merely a roof but a window through which destruction can arrive without warning, is a relatively recent revelation. It is still sinking in. For many people, it has not sunk in at all. 2024 YR4 challenged this ancient sense of celestial safety. For a few weeks, the sky contained a named, tracked, quantified threat. It had a probability and a date and a map of potential destruction. It was not abstract. It was specific. And when the threat receded, the old sense of safety returned with remarkable speed. The headlines faded. The attention shifted. The sky was once again a ceiling, not a door. But the sky has not changed. The asteroids are still there. They are still moving. They are still crossing our path. The only thing that changed was our awareness, our attention, our willingness to look up and acknowledge what the universe has always been telling us, that we are not exempt from the laws of physics, that we are not protected by any cosmic providence, that we are, in the final analysis, on our own. And that what we do with our knowledge, our tools, and our brief window of technological capability will determine whether we become the first species in the history of this planet to see a threat coming and act in time, or whether we join the long silent list of species that never had the chance. In the grand accounting of the cosmos, 2024 YR4 was a minor event, a small rock, briefly noticed, quickly dismissed. It did not strike the Earth. It will not strike the Moon. It will pass through the narrow corridor between the two on the 22nd of December, 2032, threading the needle between our world and our nearest celestial companion, at a distance of roughly 278,000 kilometers from Earth and roughly 21,000 kilometers from the Moon. It will continue on its journey, looping back out into the deeper reaches of the inner solar system, its orbit permanently altered by the gravitational perturbation of the close encounter. And then it will fade from our instruments and our awareness, becoming once again an anonymous speck of ancient stone drifting in the void. But 2024 YR4 was not insignificant. It was a message delivered in the language of orbital mechanics and probability theory and raw, unforgiving physics. The message was simple, even if its implications are vast. We are not as safe as we believe we are. We are not as prepared as we need to be. And the cosmos does not send warnings twice. The rock was born roughly 4.6 billion years ago in the swirling disk of gas and dust that eventually condensed into the Sun and the planets. It formed in the main asteroid belt, probably in the central region between Mars and Jupiter, where silicate-rich stones accumulated from the primordial material that was too stirred and scattered by Jupiter's gravity to ever form a proper planet. For billions of years, it orbited peacefully among its siblings, a mote of stone in a sparse, silent field. Then, at some point in the distant past, the gravitational resonances of the giant planets nudged it inward. Its orbit elongated. It crossed the orbits of Mars and then Earth. It became what astronomers call an Apollo-type near-Earth asteroid, a designation as bland as the object itself was consequential. For all those billions of years, no intelligence observed it, no telescope tracked its path, no computer calculated its trajectory. It simply was. A piece of the solar system's furniture, as old as the planets themselves, following the laws of physics wherever they led. And then, on the 27th of December, 2024, a robotic telescope in the Chilean desert caught it in a 30-second exposure, a faint streak against the stars, and for a few weeks, it became the most watched rock in the solar system. That transformation, from anonymous debris to existential threat and back again, is itself a kind of parable. It tells us something about the relationship between knowledge and vulnerability. Before we knew about 2024, YR4, it was harmless to us in every practical sense. It existed, it moved, it posed the same objective risk it always had. But we did not know about it, and so we did not fear it. The moment we discovered it, the risk became real to us. Not because the rock had changed, but because we had. We had acquired knowledge, and knowledge brought fear, and then we acquired more knowledge, and the fear subsided. The rock did not change its path by a single meter throughout this entire drama. We changed. Our understanding changed, and with understanding came first terror, then relief. This is the human condition in miniature. We are creatures of limited perception, living on a tiny world, surrounded by dangers we cannot see, protected only by the tools we have built to extend our senses beyond their natural range. Those tools, our telescopes and our computers and our mathematical models, are extraordinary. They allow us to detect a 60-meter rock millions of kilometers away, calculate its trajectory years into the future, and determine with remarkable precision whether it will pass safely or strike with devastating force. These are capabilities that no other species in the history of Earth has ever possessed. We should be proud of them. We should also be honest about their limitations. We cannot see everything. We cannot predict everything. We cannot stop everything. But we can do more than we are doing now. We can build the telescopes that fill the blind spots. We can fund the missions that test the deflection techniques. We can establish the institutions that make decisions in the critical hours and days after a new threat is identified. We can choose, as a species, to take this seriously, not after the next impact, now. The night sky is beautiful. It has always been beautiful. The same stars that inspired the first astronomers in Mesopotamia still shine above us, unchanged, ageless, indifferent. Among them, invisible to the naked eye, thousands of small, dark rocks trace their paths through the inner solar system, some of them crossing Earth's orbit every few years, some of them coming close, some of them coming very close. Most will miss. The geometry of space is overwhelmingly in our favor, but space is very old, and probability is very patient. 2024 YR4 measured roughly 60 meters across. It was composed of silicates and nickel iron, a fragment of the ancient solar nebula, spinning once every 19.5 minutes, orbiting the Sun once every 4 years. It was discovered, tracked, assessed, feared, and dismissed in the span of less than 2 months. And then the world moved on. But the rock did not move on. It is still out there. It is still orbiting. It will return in 2028, passing at a much greater distance. And then again in 2032, slipping between the Earth and the Moon in a passage that will be tracked by every telescope capable of observing it. After 2032, the gravitational perturbation of the encounter will scatter the possibilities of its future orbit across an enormous volume of space, and we will lose certainty about where it will be decades and centuries hence. We are temporary. The rocks are not. We build our cities and write our histories and love our children and dream our dreams, and all of it unfolds beneath a sky that is both a ceiling and a door. A ceiling that protects us, for now. A door that could open at any moment, admitting something ancient and fast and utterly indifferent to everything we have ever built or dreamed or loved. On a quiet December night in 2032, a 60-meter stone will slip between the Earth and the Moon, ancient and silent and careless, threading the needle between two worlds. And in that moment, if anyone on Earth is watching, they will see nothing at all. The asteroid will be invisible to the naked eye, lost in the vastness of the space between here and there. But it will be there, moving, turning, continuing its journey around the Sun, as it has for 4.6 billion years, as it will for billions more. We will not see it pass. We will only know it passed because our instruments told us so, and that is both the triumph and the tragedy of our situation. We are smart enough to know the danger. We are resourceful enough to build the tools that reveal it. We are, at least in principle, capable enough to prevent it. The only question, the question that 2024 YR4 placed before us, and that we have not yet answered, is whether we are wise enough to act before the next messenger arrives. The cosmos does not owe us another warning. Every generation faces threats that test its foresight and its willingness to act before the crisis arrives. Some generations rise to the challenge, others do not. The question of planetary defense is, at its core, a question of what kind of species we are. Are we the kind that sees a danger, understands it, and acts to prevent it? Or are we the kind that waits for the blow to fall and then scrambles to pick up the pieces? The answer is not yet written. The story of 2024, YR4, ended well. The rock will miss. The cities will stand. The billions of people along the impact corridor will go about their lives unaware of how close the calculations came to a different outcome. But the next chapter has not been written yet. And in that next chapter, the numbers might be different. The probability might not drop. The rock might not miss. And the telescopes that failed to see it coming might not be forgiven for their blindness. There is an image that may help crystallize the essence of this story. Imagine standing on the surface of the moon on the evening of the 22nd of December, 2032, looking up at the Earth, hanging in the black sky. The Earth would be enormous, a blue and white sphere roughly 4 times the apparent diameter of the full moon as seen from Earth. And somewhere in the space between you and that distant blue marble, invisible to your eyes, a 60-meter rock would be hurtling past at 17 kilometers per second. You would not see it. You would not hear it. The vacuum of space carries no sound, but it would be there, passing within roughly 21,000 kilometers of where you stand, close enough that the moon's gravity would tug at it, bending its path slightly, permanently altering its future orbit. From that lunar vantage point, the entire drama of 2024 YR4 would be reduced to its physical essence. A rock, a gap, a near miss. No politics, no budgets, no headlines, no fear, just physics. Just the cold, clean arithmetic of trajectories and velocities and the gravitational constant. But we do not live on the moon, we live on Earth. And from Earth, the story is not about physics alone, it is about us. About what we know and what we do not know. About what we choose to do and what we choose to ignore. About the gap between our capability and our commitment. We are, as far as we know, the only species in the history of this planet that can look up at the sky and understand what is coming. The trilobites could not do this. The dinosaurs could not do this. No creature that has ever lived on this Earth before us could calculate an orbit, build a telescope, or launch a spacecraft. We can. We are the first. And we may be the last if we squander this remarkable, improbable, fleeting advantage.